Hello, hello, um, hello, hello. Bear with me for hello. Oh, there is Avani. There is Cheska. There is Chris. Greetings, greetings. Bear with me. Good to see you. Bear with me. There is Amanda. There again. This class. I'll tell you. There is Yeyun's uh, alter ego, which is a yes. There is Yahavi. Oh my God. We're hello, Michelle. Okay, wait. I'll put on my board, but I get this class is like so. Seriously, if there was a anyway, and who else? Oh, and there is Melita. Melita, awesome. Hello. And hello. And hello, Michelle Q, if I didn't already say, who does, I think she does change her avatar every single time. I think that's enough. That should be a portal also. Oh, there's really not enough Pokemon, honestly. But okay, yes, and good afternoon, Amanda. I'm doing the chat now. Good afternoon, Hayu. Good afternoon, Marilyn. C, good afternoon, Matthew K. Good afternoon, Yeyun. Good afternoon, Yavi. Oh yeah, double. Right. Okay. Yes. Good afternoon, Melita. I'm double dipping because there's chat and there's okay. Hello, everybody. I want to get I'm also stalling because the board just did something weird. Bear with me for a minute. Yes, bear with me for a sec. But I'll tell you right now where we're going today. Is France. No, where we're going today is homework. Back to homework 8. We're going to finish the duck situation. And hello, Michelle. Yes, we're going to finish the duck situation, which is to say the physics of elevators in a way. But where is it? Okay, here it comes. And as long as, and I'll also tell you, okay, here it comes. We're still on just homework 8 for a little while. I'm not going to give it, there's just, if you have to catch up on things such as homework, or if you haven't gotten an exam back from me yet, which many of you have not, many people in other sections have, they're still coming, but we all need time to catch up. So what I'm trying to say is there's not new homework yet. Certainly not due this Wednesday. Okay, here we go. Okay, here we go. Okay. Okay. So we're back to homework 8, which is all about Newton's second law. And Newton's second law really is ultimately 3 simultaneous yet independent equations, 1 for each axis. Okay, homework 8, which I'm not screen sharing unless someone asks me to. I'm assuming you still have it. We had just done problem 4, which is the duck in the elevator. We had just done part A, I believe. Stop me if I'm wrong. And I believe the main takeaway from part A, which focus on the duck in okay. The main takeaway, if you draw the system schemas and then you draw the free body diagram of the duck, you find that normal up minus weight down equals the MA of the duck. And then you realized, and that's the free body diagram of like anything sitting on any platform under any circumstance. But the only reason to infer or believe that the normal force up is equal to the weight down is if the acceleration of that object is 0. Like what we're really trying to get across in the so when we finished part 1 of the problem, we found n minus mg equals ma. But as long as that floor is pushing up and as long as that duck is accelerating up, then the right side doesn't equal 0. So you can't say that n and mg are balanced, and you find that in fact for the duck to accelerate up, the normal force has to exceed the weight of the duck. The floor has to do more than just support the duck. It has to also accelerate the duck. Why am I making such a big deal? There's many reasons to make a big deal of this. Okay, one of the reasons to make a big deal of this is that when you draw that free body diagram, the whole thing is based on a free body diagram that comes up over and over again. When you draw the free body diagram, which basically looks like this, which does look like this, that's the free body diagram of the duck on the platform, regardless of what the platform is doing. You see two forces that are opposite. What we are trying to reinforce with this problem, among other things, is that just because two forces are opposite does not mean they're equal. And furthermore, even if they happen to be equal, that does not mean that they are an example of Newton's third law. In fact, at the risk of going back, I want to reinforce that someone's entering the room. Okay. At the risk of going backwards, I want to reinforce that that Newton's third law says if the earth pulls me down, then I pull the earth up, regardless of whether I'm on a platform or not on a platform, regardless of whether there's a floor underneath my feet or not. Newton's third law says if the earth pulls me down, then I pull up the earth, period. It also says that if a floor happens to push up on my feet, then my feet happen to push down on the floor. That's also Newton's third law. Again, what I'm just trying to say, to summarize from one aspect of last time, is that each arrow that you see in a free body diagram is an action. It has a reaction in some other diagram. Two arrows in one diagram are never, ever, ever the action-reaction pair. Newton's third law does not say that if my weight pulls me down, then something has to push me up. It's really important to understand that's not what the law says. If the law said that, then nothing would ever accelerate, right? We're not saying that just because you get pushed to the left, you must also be pulled or pushed to the right. That would be crazy. We're saying if something pushes you to the right, then you must push that thing to the left, whatever that thing is, right? It's saying that forces are mutual symmetric interactions between pairs of objects. Okay, so just because you see an N up in a diagram and an MG down diagram, you don't want to infer that they are a Newton's third law pair. You don't want to infer that necessarily they're equal just because they're opposite, right? And so in general, the other thing, I'm just summarizing like the takeaway from last time. The other takeaway is that we should never assume that the normal force is automatically present or automatically equal to any number in particular. The normal, well, yeah, I'll just leave it at that. Yeah, okay, I just want to make sure, is that, so in the case of part A of the duck problem, the normal force pushes up with a greater amount than the weight pulls down, and that's why the duck accelerates, and that's it for part. And then we got numbers. I don't remember what they are, but we got numbers for part A, and then it was over. Okay, then part B. I just want to kind of summarize. I mean, I think someone might have asked about it in this class, but I could be wrong with someone. Hold on, let me just pull up the screen. In part B is a little bit interesting, a little bit. Hold on, I'm just pulling it up. All right, part B. Consider an alternate scenario. Okay, situation's the same, but the elevator is accelerating down instead of accelerating up. By the way, if you're looking at the problem right now, which would be advisable, there is a misprint. It says the elevator accelerates down at a rate of 15 meters per second. That is literally a typo and kind of a bad typo. It really should say accelerates down at a rate of 15 meters per second squared because it's an acceleration. But okay, so you might, if you have that with you, you might want to correct it in your life. But it does explicitly say that the elevator is accelerating down. So now we have the same situation, but the elevator accelerating down. We solve it the same way as before. It would be the same free body diagram as before. Normal, because the normal is underneath the duck's feet. It's pushing, so it can only point up. Okay, and then we have gravity down. But then if you analyze it, if you do the same math that you do in part A, if you do n minus mg, and let's say we make the designation that up is positive and down is negative. And then we start solving for the normal force in this problem. Well, we get a problem. We get a fact that the normal force is negative. Now, that in itself is not necessarily a problem. Like there's no rule that says a force could be negative or positive. Negative just means what direction the force is pointing in, right? But in this case, we say that if we say that positive is up and we say that the normal force is pointing up, then if we get a negative sign in our answer, that contradicts the whole setup of the problem. Like there's something wrong there if we get the normal force pointing in two directions simultaneously. What does it indicate? It indicates that there's something we've misunderstood from the beginning of analyzing the problem. In other words, the normal force can't be pushing up on the duck if the elevator is accelerating down at a rate that is greater than 9.81 meters per second squared or greater than 10, right? That doesn't mean the situation can't happen. The situation totally can. You can have an elevator accelerating down at a rate that's greater than 10. It's just that if it is, then the floor is going to separate from the duck. The floor can no longer push the duck up if it's doing that. Just that. The floor will go down faster than the duck will go down. So as it says here on the sheet, I'm looking at two screens simultaneously again. We find that there is no, we find that n is less than 0. That means there's no contact. There is not contact between the duck and the floor. So in fact, n must be 0 in this case, right? I mean, that's a slightly subtle argument, but I'm just looking at the chat. Sorry. Okay. So you get n equals 0. And I forget what is the question actually asking for. Well, yeah. Right, so you get that n equals 0. In a moment, we'll go on to part 4 and answer how far the duck will have traveled after 7 seconds. But I just want to analyze this for a second, like for a moment. Yeah, I mean, in part B, according to the facts, well, I think I just said this, but the elevator accelerates down at a rate that's greater than free fall, therefore greater than the duck. So there's no contact between the duck and the floor. So what? Okay, so the answer is that n equals 0, kind of like it's explaining the problem. But so what? Like, why are we putting you through this? So what? Well, number one, I'm going back and forth. Number one, this reinforces something I'm trying to say over and over again, that the normal force means, like triple equal sign, it means a push, i.e. a contact from one surface onto another, perpendicular to the plane of contact. If there is no contact between the surfaces, then there is no normal force. Like what I want to say over and over, because honestly, again, I mean, sort of like this is like a classic area of difficulty for students of physics and for teaching physics. The word normal means perpendicular. It does not mean typical or regular or common, but it always feels like it does unconsciously. I just want to enforce again that normal, like don't think that just because there's a physics problem, there has to be a normal force in it. Or just because there's mg in a physics problem, there has to be normal force. No. Normal is there if and only if two surfaces are pressing against each other. When one surface presses against another, perpendicular to the plane of contact, that's what we call the normal force. If you want to think of it as like pressure between surfaces, that's what the normal force is. If there aren't surfaces and they aren't touching, pressing, then there isn't normal. Like for example, like a fish hanging from a fish line. It's a perfectly reasonable physics problem. You could do all kinds of things with a fish hanging on a fish line, but there's no normal force there at all, right? Or something in free fall. There's no normal force there at all. Okay, so we're just trying to say here, number one, please don't think of the normal force as something that's automatic. Normal means perpendicular. You got to see two surfaces pushing perpendicularly on each other for there to be a normal. Okay, I think I've said that a million times, but that's part of what this problem is trying to say. But then also, quite frankly, I'm going to get myself into trouble with this, but I also want to make clear that, okay, if something's in free fall, if the only force acting on something is gravity, then something freely falls, and it falls at a downward acceleration rate of 9.81 meters per second squared, approximately. Okay, fine. We can stop things from falling by putting like a table under, I could put a table surface underneath a pen, and then the pen doesn't fall. First thing to be clear is when we put a tabletop underneath a pen and stop the pen from falling, just to be explicit, we're not removing gravity, right? Gravity, like we're not removing the weight of the pen. The weight of the pen is still there. The center of the earth is still pulling the pen down. It's just that now we're introducing another force, a force that's going up. We're intentionally introducing another force, a force that pushes up, so that the net force, the sum of all the vertical forces, a positive plus a negative, yields 0, and then the pen doesn't accelerate at all. In other words, the way we fight gravity is we literally fight gravity. We don't remove it, we counteract it, right? The desk does not interrupt the flow of gravity. Now, similarly, if you accept that, which I think most of you do, if you understand that, like, you know, we can fight gravity with an upward force. We can even exceed gravity, right? Like we can put that table that the pen is on into an elevator. The elevator can go up, and that just means now the table is exerting an upward force that's more than the weight of the pen. Okay, like just like we did with the duck a minute ago, fine. But please understand then that there's no rule going in the opposite direction. We can, just like you can pull something up at a rate that's greater than 9.8 meters per second squared, you could certainly pull something down at a rate that's greater than 9.81 meters per second squared. There's no rule against that, right? That's just what happens when things are only subjected to the force of gravity. So we can pull something down, like this elevator in this duck problem. We can pull the elevator down at a rate that is greater than the free fall rate. And I mean, the thing that we're pulling down in this duck problem would be the elevator, the cage, the floor of the elevator is going down in this problem at like 15. Okay, so it's no longer touching the duck, but the ceiling will hit the duck's head, presumably, right? And that's all fine. That's not a contradiction of anything. I'm pointing that out because that was part, I know we're still getting the midterm exams back, but I just want to say, like, that's what was happening in that problem on the midterm with the helicopter, on not on the practice, but on the actual thing. The helicopter was accelerating. Well, the helicopter was moving up at a certain instant in time. It had an initial or instantaneous velocity pointing up, but at that moment, it had an acceleration down. That's not a contradiction. That might be interesting. That might be challenging, but that's not a contradiction. And when the rope was cut, or whatever, when the package was released from the helicopter, the package began to free fall down at the standard rate of 9.8 or round it to 10. And the helicopter was accelerating down at a greater rate. Two things just to be clear. Three things. Number one, that's okay. That can certainly happen. Number two, they both were velocitizing up while they accelerated down. That's not a contradiction either. That's just like throwing an object up. It has an initial velocity of up, but it has an acceleration of down. So it takes a while before so if you throw something up, it goes up for a while until it reaches 0 velocity, and then it starts coming down. So it'll take a while. If you throw something up, it takes some time before it's below the place that you threw it from. Kind of like, in fact, the first problem on the midterm, like the purple plushie going off the building, right? Things will go up before they come down if they have an upward velocity and a downward acceleration. That's what the helicopter and the package both do. Only the helicopter in that problem is accelerating down at a greater rate. So just to say, I mean, maybe I shouldn't be talking about this, but I've noticed there was just to say then they'll both go up for a while, but then they'll come down. But all of that will happen more dramatically for the helicopter than for the package. So I think the helicopter ends up being below the package in that. And that's not a contradiction. Helicopters, whatever mechanism they use to push air to go up, they can use that to go down. Like otherwise they would never land. I don't mean that to freak anybody out, but so that's what's happening with the duck here. The elevator is going down at a rate that's faster than the duck is. So they lose contact with each other and the normal force is 0. Okay. That's the point of that. And certainly if there's questions, I'm happy to answer them. I'm looking in the chat. There don't seem to be. Okay. But then so then it asks, again, for anybody who just joined or attentionally just joined, I'm in homework 8. I'm in problem 4, the duck elevator problem. I'm in part B at the end, like little Roman numeral 4, where it says, so under these conditions, how far will the duck travel in 7 seconds? Okay, so now that the elevator is, and it even sort of hints or helps you by saying, imagine that the ceiling is not an issue, like that there's no ceiling in this cage. So, okay, so that's a hint about something. It asks you what the duck will do in 7 seconds. So now the forces are gone. There's no normal force anymore. It's just a free fall problem. So now it is like earlier in the semester. It's just a matter of acceleration. The duck is accelerating down at a rate of 10 meters per second squared. Now here I decided to call down positive, actually because for no good reason, but I can if I want to. And therefore I call up negative. You can flip it. You'll get the same. If you are consistent, you'll get ultimately the same answer as I did. But that's the way I did it. So then it's just a kinematics problem. You have a package who's you have a duck, which is in free fall. So its acceleration is approximately 10, but its initial velocity is 50. So I get negative 105. In my system, negative means up. So I find that the duck goes up 105 meters from where it was when this situation started, right? It goes up. Now let's be clear about that for a minute. The duck is in free fall, but it ends up above where it started. Is that a contradiction? No. Is that something we want to understand in physics? Yes. It's why one of the early homeworks was called free falling up. I want to make it clear that when you're in free fall, that doesn't mean necessarily that you're velocitizing down. It means you're accelerating down. Free fall means you're accelerating down. You could be at that moment moving up. You could be moving to the side, like a projectile problem, like lab number 4. Like lab number 4, right? You could be moving in any kind of direction while in free fall. It just means, right, as long as someone thrusts you with some initial velocity, you could be doing anything. But it means that at that moment, the only force on you is gravity, is your own weight. So the only acceleration you're experiencing is straight downward, 10 meters per second squared. So what I'm trying to say is this duck, it has an initial, like the moment this problem started and the moment we started paying attention to it, the duck already had an upward initial instantaneous velocity of 50 meters per second, right? It was just like the helicopter in the package in the other thing. The duck was already moving up at 50 meters per second when the elevator left it. So it's free falling, but with an upward velocity of 50 meters per second. Well, free fall means that every second you lose 10 meters per second of your upward velocity, right? So what I'm trying to say is this duck is going to take 5 seconds to keep going up until it runs out of speed entirely, right? Like this is like the early problems on the midterm. The duck is not even going to start coming down for 5 seconds. Then it's going to take another 5 seconds to come back down to where it started. If we let this duck go for exactly 10 seconds, our answer would be that the duck went nowhere, right? Its displacement would be 0, just like the package in the helicopter problem from the midterm, right? If we gave it exactly 10 seconds, where am I getting this from? Because its upward velocity is 50, and every second it loses 10. So it would take 5 to lose and 5 to come back, right? If we gave it 10 seconds, then it would be right back where it started from. Any more than 10, it would be below where it started. But any less than 10, as we gave here 7, it's somewhere above where it started. It's just if nothing else, and I'll move on. I'm not trying to yell. I'm not saying anybody got this wrong or anything like that. I mean, I think there was, but whatever. I'm trying to, I guess right now I'm reinforcing that acceleration is related to velocity, but they're not the same thing. And to really see the difference between velocity and acceleration is a big, big part of physics. It's not easy, but it's like central. All right. So anyway, that's the answer to that. I'm just looking, there's a chat. I can't get my chat confused with doesn't look like there's anything in the chat. Okay. But if there is, please let me know. Okay. So the next. Then the duck gets on a scale. A scale? Like what? How is there like a scale? And yes, there's my artistic render. Okay. But the duck is now on a scale. And I mean like a bat. I don't mean like Libra, like I don't mean like the scales of justice. And I don't mean like a inertial balance. I mean like a platform, like bathroom scale. So basically like just like a square that you stand on, and it tells you a number, right? Now, it says here in the problem, it tells you that the scale registers 720 newtons. Well, first of all, wait, what newtons? What scale? Well, yes. Remember, scales are supposed to tell you something about like weight or something like that. And remember, weight is a force. Like scales don't register or at least these kind, like spring scales don't register mass, they register force, i.e. weight. If you're American, maybe they call it pounds. But if we're in the metric system, they call it newtons, and there's a conversion factor between the two. But okay, so the scale apparently says some number of newtons, 720 newtons. And then it asks, based on that, figure out the acceleration of the duck. Now, that may seem like an out of nowhere, like what? I mean, how does that have anything to do with anything? Well, good question. Let's talk about what scales do for a second. And again, I'm picturing like a bathroom scale. I'm picturing like some platform that you stand on, it has like springs in it. You stand on it and you push the springs down, and the more you push the springs down, the higher number the scale registers. That's what I'm picturing. Okay. Remember, the downward gravitational pull from the center of the Earth acting on a mass is what we call weight. Strictly, right? Weight is the force of gravity, m times g. Right? Again, mass is measured in kilograms. Weight is measured in newtons. Mass is your resistance to force, but weight is a force. I mean, that's a subtle distinction you might want to think about. So weight, your actual weight is mg. But what is a scale measure? Well, a scale doesn't know a scale is not at the center of the Earth. A scale is not registering how much you're being pulled through empty space to the center of the Earth. What a scale is doing is what I keep on saying. It's responding somehow to you pressing against the scale, right? You're standing on the scale, pressing down on it, and the more you press down on its springs, the higher number gets. So a scale is not registering a pull, it's registering a push between two surfaces, the surface of your feet and the surface of the scale. So if you think about it, you push down on the scale, right? And by Newton's third law, like what I was just yelling about 5 minutes ago, the scale pushes up on your feet the same amount, right? I'm saying I don't, this is a subtle point. I'm saying mg and n are not always equal and opposite, but n is always equal and opposite to itself. Whatever you push down on the scale, it must push up on your feet. That's the interaction between you and the scale, and that's called the normal force going in both directions, right? One of those arrows is in the diagram of you, or the duck. The arrow that's going up is in the diagram of the duck. But if we drew a diagram of the scale, there'd be an arrow going down on the scale from the duck. I hope that's clear, and stop me if it's not. Why am I saying all this? Because I have no life. No, I'm saying all this because what the scale actually feels and reports to you is the normal force. It's feeling the normal force you exert on it, but then it's displaying the normal, it's feeling the normal force that you press down on it, but then by registering that number, it's telling you the normal force that it exerts on you. Newton's third law. Right? Oh, there is something in the chat. Sorry, hang on 1 second. There's something in the chat, I think. Thank you. I'm not even sure what. Okay, thank you. I'll take it. Great. Awesome. I don't even remember. That's how freaked out I am. I don't even know what I said. Okay. Okay. So the scale readout is in newtons. I mean, if it's a metric scale, right? The scale readout is in newtons. It's not telling you your kilograms. That would take like an inertial balance. It's not telling you, strictly speaking, your mg. We might be it's not strictly telling you your weight. It's telling you the normal force that you exert on it. If you're really getting this picture for me, that normal force is two things pressing against each other, then that's what the scale is telling you. In fact, by the way, the flip is, if this scale picture works for you at all, like if this makes any sense to any of you, what I'm saying about scale, then that also from now on, that's the way to think of a normal force. A normal force is like what you would do to a bathroom scale. Even if the bathroom scale is tipped on its side and you push into, like it's on a wall for some reason, and like you put your hands against it and the number gets higher and higher, yeah, what it's telling you is the normal force that you're exerting on the scale. Like that's what normal force is. It's just two things, two surfaces pushing against each other. Okay, so now what I'm trying to say is, then what the scale reads technically is your normal force. Indirectly from that, we infer your weight. I'm trying to say right now, very carefully or very explicitly, what the scale is your apparent weight. It's what your weight appears to be. Why am I saying Okay, I'm saying it might not be your actual weight, what the scale says. It's what your weight appears to be, given a very certain assumption. The assumption is that we're not accelerating. Like, let's be clear about this. If you go into your bathroom, I mean, or your bedroom, whatever, like you go into your apartment and it's like a normal day and you're in your apartment and your apartment is not accelerating up, it's not a rocket ship, accelerating away from the center of the earth. And you walk over to your scale and you stand on it. The first thing I'm saying is what your scale feels and reads is the normal force exerted by your feet. And if you do the free body diagram of you, it's just like the free body diagram of the duck. The normal force is pointing up, your weight is pointing down. And then, okay, if it's a typical everyday day and you're not in a rocket ship, then A is 0, right? And if A is 0, if and only if A is 0, this is what this is trying to say, then the normal force will be equal in magnitude to the weight. Okay, so if you look at the scale and it says you weigh 180 newtons, right? What it's really saying is we feel 180 newtons of press of the normal force here, and we're reporting 180 newtons of normal force pressure here. If you have good reason to believe that you're not accelerating, then you can assume that your weight is perfectly supported by that upward force that we are exerting on you, we the scale. If you're not accelerating, if and only if you're not accelerating, you can assume that those two are equal. Therefore, by reporting to you the normal force that you are exerting on us, and therefore we're exerting up on you, you're safe to assume that that actually corresponds to your weight, assuming you're not standing in an elevator or in a rocket ship, right? So it reports the apparent weight. Indirectly, we infer that's our actual weight, assuming our acceleration is 0. I hope that's clear so far. Like, in other words, it's not Newton's third law, it's Newton's second law, right? The fact that N is equal to mg is Newton's second law, assuming A is 0. But if A doesn't equal 0, which I keep saying rocket ship, but which is perfectly possible, like if you're in an elevator, if you're the duck, if you put a scale in an elevator and the elevator starts accelerating up or down, then the normal force doesn't equal the weight. And what I'm telling you right now is it's not just about ducks. I mean, it's not all about ducks. I am telling you that we have a bathroom scale in the physics lab, where we used to. I believe we still do, like up on one of the shelves, like right near the door. I'm possibly about to get myself in trouble, but it seems to me that if you have like a couple of minutes or break time or something during your next lab, I mean, I believe the Walters won't, or I believe Mercedes would be okay. I mean, I'll talk to her. I mean, Professor Talley would be okay. I think if you take 10 minutes and go to an elevator with that bathroom scale and you stand on the bathroom scale in the elevator, I'm like worried to look at what's going on in the chat right now as I'm saying this, but I can't speak for Professor Talley. And but I can tell you, if you bring that bathroom scale into the elevator and you take a couple of rides in the elevator while standing on the scale, absolutely the numbers will change on that. There's nothing magic about this or hypothetical. The numbers will change on that scale as you ride up and down. Now, let's be specific. Yeah, I know. Honestly, before COVID, I used to take whole group. I did do this. And I would take whole groups in the elevator one at a time with the scale and have people stand and do different things. And yeah, everybody thought we were weird, but they were right. We are. Now I'm not going to, we used to like literally do a whole lab on this. I mean, it was a little bit over much. Yes, people will think you're weird, but I mean, who will? The criminal justice majors? I mean, whatever. Oh, I did not just say that. Oh no, I didn't. Okay. Maybe you'll run into some forensic psychology majors and they'll think you're weird, but then they'll help you. Okay. My point is the numbers really will change on that scale. In fact, this starts to be the question. I mean, it becomes the next question in the whole thing. But just to get numerical right now, if the elevator, if the scale is, if the elevator, when the scale is not accelerating, when it's just moving, then nothing interesting happens. And this, again, is the whole Galileo thing. I don't care how fast the elevator is going from the 2nd floor to the 8th floor or something. I don't care how fast it's going. If it's cruising at a constant velocity, no matter how high V is, if A is 0, then you don't feel anything. this is the Galileo thing. You can't tell whether you're moving past the floors or the floors are moving past you. Your stomach feels fine. You could play sports and then you get really weird, but you could like play sports in the elevator and you don't have to adjust your throw, or you could dribble a basketball. You don't have to adjust your dribble when you're cruising, right? It's just like being in an airplane cruising. But once the elevator is leaving a low floor and speeding up, i.e. accelerating up, then the scale will push harder against your feet. Your feet will push harder against the scale. And absolutely, while you're looking down, you'll see the needle will point to a higher number. And that's when you often feel it in your stomach. I mean, depending on who, we don't feel velocity. We can't sense or test for velocity. Velocity is in the eye of the beholder. But acceleration is always accompanied by net force. So we feel the effects of acceleration. I mean, feeling, but we sense, both like in our stomach, depending on who we are. But I mean, like the data is different for accelerations. This is the point of Galileo and Newton. The scale, okay, I'm saying enough of this, but like the scale will be different. And how different will it be? Oh, sorry. Wait, okay. Okay, wait. Right. Okay, cool. Right. Yes. Just tell them it's for science. It's okay. Everybody believes in science now, except for people that don't, I suppose. The question you all saw the thumbs up. Right? Did I see the thumbs up? I'm not sure I did, but okay. Yeah, no, I highly encourage you to do it. And then also when people are like, look at you, like, what do you mean science? Then be like, fine, go get COVID. What? I didn't say that. Okay. So I really didn't actually.
Can you go back to the slide before for a second, please?
Absolutely. I thought she was gonna say, can you go back to the inappropriate joke from before? No, sorry. Yes. Hold on here. Wait. I know I don't know why the Zoom is so weird. Okay. Yes. And tell me when. And thank you for using your voice to say that too. I totally appreciate it. It's good.
Can you just explain the point at the end? It will, like, when it's accelerating vertically, it will not read exact weight. That's like when you have acceleration. That's what you were saying on the page before.
First of all, thank you for stopping. Thank you for asking and clarifying, because it is a big point. Yes, that is what I'm saying. And I think in a moment, it might even be clear when I show you the numbers or the math, which I will. And it might in particular be, I know that makes it more concrete for many of us. But yes, I am saying, well, here's what I'm saying that like last week, we said in order to accelerate up, the floor underneath you or a duck or whatever, in order to accelerate up, the floor must push up more than your weight pulls down. Like the floor, just to support you, has to exactly support your weight. But if it's going to shove you up, it has to push harder. And it can't just match your weight. It has to push up with a force that's greater than your weight. That upward force, I'm saying, is the normal force from the floor. And what I'm saying is that's what a scale would read if you stood on a scale. So yeah, I mean, I will flip the page in a minute, and I think it might be more concrete, like when I show you the equations and stuff, but it might be. But yes, I'm saying that when an elevator accelerates up, if you're standing on if you just get on a bathroom scale in an elevator, and I mean, all joking aside, but to everybody, the reason I'm talking about that you have a scale in the lab and you go do it is because I'm trying to say this is not a hypothetical, or this is not a, like an idealization. This is just like really concretely true in the real world. If you're standing on a scale in an elevator, when you stand on the scale, it reads your apparent weight. When you press the up button and it starts to, and it's speeding up, like before it reaches a cruising speed, you will see that needle on the scale move substantially up. Like your weight will seem to be greater. And when the thing accelerates down, you'll see your weight go down. That is what I'm saying. And so here's maybe the more concrete part. Or I don't know if that, but Melita, maybe tell me if that, wait, what?
Yeah, that makes sense. Thank you.
Okay, cool, thanks. Whatever the professor drank, I want some. Whoa, now you know what I drink? I'll tell you right now. This is like a not paid for. I should like monetize. No, I can't. What I drink is one too many Celsiuses in a day, and I drink just enough Celsiuses that they really should measure my beverage intake in Fahrenheit. That's all I'm saying. Okay. Or Kelvin. Oh my God, 270. Okay. Anyway. So what I'm saying on the next page is they tell you in the duck problem, they say, assume that the normal force or that the scale reads 720 newtons. What I'm claiming to you now is if they say the scale reads 720 newtons, that means the normal force exerted up by the scale is 720 newtons. Like that's what I'm saying. So then how can you figure out acceleration from that? It's the exact same free body diagram and the exact same Newton's second law as before. N minus mg equals ma. Just like before, the whole key is to understand that a now doesn't equal 0. We're going to solve for a, but we know what the normal force is. The normal force is 720. Your weight, so the normal force is your apparent weight. It's what the scale says you're weighing. 180, like 18 times 10 mg, that's your actual weight. One is how much something's pushing up against you. That's what you feel. And one is how much the earth is pulling down on you. That's what is true, but you don't feel. The difference between the two of them, divided by mass, is accounted for by your acceleration. So here's the math. Like acceleration equals the normal force minus the weight all over m. That's in English. So the normal force is 720 newtons. That's a higher number because you're accelerating up. Your weight is 180 newtons. Okay, so the difference between them is 540 newtons. And you divide by the mass. So in this case, the answer is 30 meters per second squared is how fast the elevator is accelerating up. If it had accelerated down, the scale would say something lower than 180 newtons. I don't know if that's, hopefully that's clear. There's more. Oh, I'm just going to pull up the other screen now. The other screen. Sorry. Okay. This is. Oh yeah, right. So this is all part C. I'm sorry. I don't know if I said that. This is all part C that I'm talking about. And we just got the answer to part C, the accelerate. So yeah, I mean, so this is, I think I did say that. This is part lowercase Roman numeral 2 of part C. So we got the acceleration of the duck. The upward acceleration is 30 meters per second squared. Then it says part D, reflections. This is what I was just like yammering about at the top of my lungs for 5 minutes. It says, how does the acceleration of the elevator affect the normal force of the duck? The normal force on the duck. The greater the upward acceleration, the greater the normal force on the duck must be. That's what we're saying. Then it says, how does the velocity of the elevator affect the normal force of the duck? I'm saying it doesn't affect it at all. Velocity does not affect forces. Velocity is not something we feel. F net does not equal MA. F net equals MV. Hugely important distinction. Again, I can't, for the rest of our lives in physics, velocity is in the eye of the beholder. Velocity is a matter of perspective. The velocity of an object is always in relation to some other object. And depending on what you're comparing it to, you get different numbers. But acceleration comes from forces, interactions. So accelerations we can measure and feel and sense. Then part E asks more sort of verbal reflections on the thing I was just talking about. So I'll just say it quickly. I mean, and stop me if you want me to slow down, but I think I just said all this. It says here, I'll screen share quickly just so you see where I am. Hold on. Okay, so I'm in part E now. I'm just going to say the answers because I feel like I just did. When the elevator is first starting to move, what kind of acceleration does it have? Upward, downward, or none at all? When it's first, now you said you pressed up. Like that's important. You're in the elevator, you press up. So it's starting to move up. So it's moving up and it's speeding up. So that means it's accelerating up, right? It's upward acceleration. At this time, you would feel heavier. And the scale would say a heavier number. You would feel like that's that feeling that you have in your stomach. Like if you do get it, I mean, not everybody does, but you're being squeezed against the floor. Like what we're trying to say here is going up doesn't mean anything. Going up just means the building's going down compared to you. There's nothing for your body to sense or feel if you just go up. But if you're accelerating up, the only way that works is the floor must be like pressing against your feet more. And then your feet, and that contact pressure is being transmitted up through your body. Like you're being squeezed. Not when you move, but when you accelerate, you're being squeezed. And that's what you feel. And it feels heavier. I mean, metaphorically and literally. Then when the elevator, so the answer to 2 is heavier. When the elevator is in the middle of its journey, what kind of acceleration does it have? Like none. I mean, once it's cruising, it has no acceleration. So you feel normal is the next question. Then when the elevator is coming to a stop, but it hasn't quite stopped yet. So now assuming it's still going up, but it's slowing down. Now the acceleration is downward. Now you would feel lighter. And let me add one thing to that, and then we'll move on. I mean, okay, then it says, do you see connections between here and part D? Like, hopefully, yes, because that's like what I'm yelling about. But I also want to be clear now when the elevator starts going down, again, it's about acceleration. It's not about velocity. So now if the elevator starts going down, when it's speeding up while traveling down, right? Like, so now if you press the down button and you leave a high floor, just to be totally clear, picture it. When the elevator is gaining speed while going down, that's downward acceleration. That's downward acceleration. So you'd feel lighter, right? And when it's slowing down while going down, that's upward acceleration. You'd feel heavier. So again, don't just think of it as like speeding up versus slowing down. No, it matters. It's negative versus positive acceleration. When you're slowing down while moving down, that is upward acceleration. If that's, and maybe that, I mean, that is a little confusing maybe, but think of it this way. When you're going down and slowing down, like the platform below you is putting the brakes on. If you're slowing down while you're going down, that platform, the floor, the scale underneath your feet is coming up against your feet. It's sandwiching you more. I can't say it any better than that, but think about it. So slowing down while going down is the equivalent experience to speeding up, going up. Either way, the sandwich, the pressure between the floor, the scale, and your feet is greater in either case. The weight would be registered as higher. And honestly, you can test it. I'm not telling you to do what to do with Mercedes, but like if you did take a scale into the elevator and try all these 4 different cases, you should get 2 cases of the number going higher and 2 cases of the number going lower as described. And it will, it'll be dramatic. Okay. Wait, was there anything more? Oh, sorry. Okay, I'm going to screen share back. I mean, I'm going to go back to the other. Is there anything in the chat? No. Okay, I'm going to go back to the other screen now. I know we want to move on this one, but there's actually more, even believe it or not, to be. Oh, wait, I didn't. Hang on. Sorry. Okay. We're back. Okay. Well, here. So where we were a second ago was right here, right? That's where we just finished. Now I'm moving on to the next thing. All of what so I'm still on this problem. I want to say one more thing about it that I think is worth saying. Is interesting, I think. So due to all the above analysis of the normal force and apparent weight, which is what we're saying ultimately your apparent weight, what you measure with a scale, is not directly your actual weight. It's your normal force. And that does indicate your actual weight as long as you're not accelerated. But if you're accelerated, the number registered on a scale is not your actual weight. And furthermore, what we're arguing here is whatever it says on the scale is a more accurate reading of what you feel. It may not be what the earth is actually doing to you, but it is what you feel. So this is all why when we're in free fall, which is part B, right? Part B, the duck, all like the elevator like leaves the duck, so to speak, and the duck is now in free fall. Well, according to this whole analysis, then the normal force exerted by the scale on the duck then is 0, right? the scale's not in contact with the duck anymore when they're in free fall. And that would be true if the duck were standing on a scale and just fell off the top of a building. Then the scale and the duck would separate, right? They have no reason to be pressing against each other anymore if they're in free fall. So the scale would register 0. So the duck would say, we would look down the scale and the scale would be saying, you have no weight. And the duck, in fact, would be saying, I feel weightless. If you've ever heard of this concept of apparent weightlessness, this is when we experience weightlessness, when we're in free fall, according to this whole analysis. And I want to pause on that because I think that's very interesting. When you're in free fall, by definition, means when the only force acting on you is your weight, right? When you're in free fall, the only thing acting on you is your weight. So you'd think, well, I don't know what you would think. I would have thought that would mean, well, that's like the most weighted scenario I can imagine because weight is doing everything and nothing else is doing anything. But no, when my weight is the only thing acting on me, when I'm in free fall, that's what we call weightlessness. Why? Well, partly because of everything I just said. A scale would say that you have no weight, but also you would feel no weight. What do I mean by that? I mean, let's imagine that you fall off the top, but you're standing on a scale and then you or someone like slides you off the top of a building. I don't know, it's like Minecraft or something. It always goes back to it, right? But like someone, let's imagine there's a big cushy pillow or a huge purple plushie at the bottom, or it's the Garden of Banban or something like that. No innocents are going to be hurt in the making of this fictional video, is what I'm saying. Let's imagine that you freely fall down a really, really long descent, and you're going to be safe when you hit the bottom. And it's going to be so long, it's like Alice in the rabbit hole or something, that you want to get cozy and maybe chill out, maybe even do a physics experiment or two while you're in free fall. So you got pushed off the top of this building while you were standing on a scale, and like Alice, you have like a pot of tea and a cup with you for this journey. So you fall off just bear with me. Talk about drinking, yeah. But no. You fall off the building. The scale was underneath your feet. Now it's separated from your feet. So the scale says 0. And you're like, that's curious. Weightless. Do I really feel weightless now? In what sense am I weightless? Here's the sense. You start pouring the tea, right? You have this pot of tea. It's got tea in it. It could be any beverage, any fluid. It doesn't matter. And you start pouring into your cup. And what will happen is it won't pour into your cup, right? It won't. You'll be like an astronaut. Why? Well, I mean, the tea will fall. I mean, you'll tilt the pot and the tea will fall down at the rate of 9.8. So why shouldn't it go into the cup? Because the pot and the cup and you are also all falling at a rate of 9.8 meters per second squared toward the ground, right? This is relativity again. If you're all falling at the same rate, then nothing is going to fall relative to anything else. So you're going to have a totally different experience from what you do when you're on the ground, right? The tea won't pour. And there's other examples, or if you try to dribble a basketball, it's going to be totally different. The basketball, you let go of a basketball, it's going to just hover with your hand, right? I mean, it'll be like a tiny bit separated because the electrons will repel. It'll be a tiny bit, but it's just going to hover there. The basketball is totally plummeting, but so is your hand, right? So everything is going to like float with you while you free fall. It's going to look just like those pictures of astronauts in a satellite. I want to make clear right now that, yeah, astronauts in a satellite, in a space station. The reason everything looks like that, all weightless and weird and floaty and everything in a satellite, is not because there's no gravity. There's totally gravity in outer space. There's gravity everywhere. Gravity is weaker, like far from the Earth than it is near the Earth, but it's also stronger, closer to Jupiter. That like, it's not because gravity disappears or even is a weaker number. That is not, it's because everything is subjected simultaneously to the same gravity. A satellite, by definition, and we'll deal with the details of this more in the next unit, a satellite is, whether it's a natural satellite like the moon, or a person-made satellite like the space station, a satellite is not a rocket ship. It doesn't use fuel to stay in orbit. It just uses gravity to stay in orbit. A satellite, like the moon, is something that is perpetually, continually falling freely toward Earth. It might be velocitizing off to the side, so it might keep falling in a circle, right? Remember, we said this 20 minutes ago, and that's the case. Like the moon has a tangential velocity, so it's moving like that way while it falls this way, but gravity yanks on it while it's moving that way. So then like the gravity pulls down on its horizontal velocity vector and yanks its velocity vector a little bit to a diagonal, but then now it's on a diagonal, and now gravity yanks it again toward the center of Earth. So whether it's the moon or an artifact or the space station, what you have is something that is perpetually accelerating in free fall toward the center of a circle while it velocitizes off to the side. So it never gets to Earth, it never velocitizes in towards Earth, but it perpetually accelerates towards Earth. Again, very important distinction between acceleration and velocity. But once you have something like that, once you have the satellite that is in perpetual free fall, then everything inside it is in free fall. So everything inside it is weightless, not because there's no gravity, but because everything is freely together experiencing gravity. So nothing is experiencing gravity relative to anything else. It's all about relativity. Excuse me. So bottom line, free fall is weightlessness. That, and just to tie this all together, I don't know if that, and that's what was happening to the duck when in part B. All right, I don't know if that helps or not, but all right. Now we go to the next problem. Hold on, I'm just looking at the time. Okay, 15 minutes. But stop me if that. I hope that was clear. Okay. Homework 8. I mean, problem 5 now. The double block. I don't know why that's got erased. The double block in homework 8, problem 5. There's a lot going on in this problem. There's 2 blocks together. They're on a rough surface. When this problem was assigned, it was before we got into the details of mu times the normal. So in this problem, it sort of apologetically explains that it just tells you frictional forces. It doesn't expect you to calculate them from mu or anything like that from here on in. If you had a problem with friction, you like would have to calculate it from mu. But anyway, we've got these 2 blocks together on a table. The table is rough. And we're also told that there's like a hand pulling the blocks to the left, right? I believe. Yeah, it says there's a hand trying to make the blocks go to the left. So I think the easiest way to picture that is the hand is pulling. So like there's like it's not a normal force, it's not a push, it's a pull of some sort of one-dimensional object. So it's some kind of tension that the hand is exerting to the left. You don't have to use that word if you don't like, but that's, I think, what it is. So then first in part A, it asks you to draw a system schema of this situation. Now, what is a system? Just to be clear, like we could choose to analyze M1, and maybe we do at a certain point in the problem. We could choose to analyze M2, or we could choose to analyze them together as one system. We can set our zoom, so to speak, to whatever level we want in physics. It's like one of those many choices that we make in physics all the time. When you're starting a problem, it's advisable. It's most, the simplest thing to do is to zoom out at first as far as you can, to regard as much. In other words, when we do physics, we're not looking at each individual electron in each one of these blocks or each individual like molecule or atom or anything like that. We're treating the whole block as one, even though it's got tons and tons of little like atoms that it's made up of. Well, similarly, if we've got 2 blocks next to each other, to the extent that we can, when we first start looking at it, we would probably like to just collect the 2 blocks in our mind and call it one system or one big particle. We always do that. We can zoom out as far as we can, as long as, I think that's what it says here. Yeah, we can choose to collect as many M's into one system as we wish, as long as they, if and only if they all share one value for acceleration. Once one thing is accelerating different from another, well, then it's 2 different F net equals MA. Then it's 2 different M's. But as long as there's one A that can be applied to a bunch of M's, we treat them all as one big M. So here, at least at this stage in the problem is asking us to do a system schema of the whole combination, okay? So here, I'm just going to change the view of the screen. So here is the system schema of the whole combination. First, as the center of Earth is an object pulling on the system. That's always there. I put it wherever I want because I don't care about direction and these things. And it's always connected by one line. Gravity pulls without touching, so it gets one line. Then there's the hand is pulling on the object also. That obeys the one touch, one line rule. So it's there as well. The hand is pulling on, and again, this doesn't care about, this is just to identify how many forces there are. It doesn't matter about direction. Then the table is in contact with M1 and M2, right? The table is a surface pushing up on the bottom surface of M1, M2. So its surface is pushing. So this is, so its surface is pushing, and the problem made explicit that friction is going to be an issue here. Like, it mentions friction. It might have done it a different way. It might have said the surfaces are rough or something like that. But as long as you know that you've got surfaces pushing against each other and they're rough or they're frictional in any way, then two surfaces pushing on each other always interact in two ways. Two lines go in the system schema to indicate that there's going to be two forces once we make the free body diagram. So now I go and I make the free body diagram, and indeed, there's a normal force and a friction force from the table, and they're perpendicular to each other as always. And the friction is parallel to the plane of contact, the normal is perpendicular to the plane of contact. And then you've got mg down, but it's the full m. It's M1 plus M2. So there's different ways you could write it, but I'm writing it as M1 plus M2 times G. And then you got the force of the hand pulling to the left. I mean, you could call it the hand if you like. I think it's a tension force. I think that's just as valid and possibly more clarified to call it tension, but there it is. Those are the four forces. Now, I have no reason to believe those horizontal forces are equal. I assume, in fact, I may have there's a hold on. I'm just saying, what was the problem say? Yeah, I mean, if I read the problem, there's all this talk about the system traveling in 7 seconds and all this stuff. And it's talking about the sliding or kinetic friction that opposes their direction of motion, right? So all of the implications of this problem, I mean, all of the words of this problem imply that the objects are sliding, are moving along the surface. Therefore, that hand must be winning the fight to accelerate these objects. So the leftward tension force from the hand has got to be greater than the rightward force of the friction. Oh, and especially because it says that the whole thing accelerates and everything. So yeah, so I believe the leftward force is greater than the rightward force. We'll figure out the numbers in a moment. But it is purely sliding. It's purely horizontal. So I do think that the upward normal force, it's probably fair to believe this, the normal force up from the table supporting the whole system is perfectly matching the downward weight of the whole thing. So that's my free body diagram. Okay. I'll keep going. Ooh. All right. Okay. So C asks, what's the normal force? Well, yeah, I think so. I do. So I look at my now. Oh, I should say this. Now that it's getting into forces and accelerations, if I had any forces at all pointing in any kind of angles, which is like the next thing we want to look at again in detail. If any forces were going off at any angles or anything like that, I would have to resolve them into components first before, like, we need a component diagram to start solving F net equals MA. But here, everything is, all the forces are along the X and Y axis. So I have the luxury, there's no angles here. So I have the luxury of already having X and Y components. So I'll look at the Y axis to do this. The Y axis. In other words, I'm doing this. right? And the sum of the forces on the y-axis is N minus M1 plus M2G down. Or you could make it two different forces if you want, but whatever it is, I think they're equal because we're not in an elevator. I don't think the thing is accelerating up or down. So I think in this case, we could say this. Or if you like, or equivalent, you could say this. I mean, exactly the same point, right? And are we given numbers? Are we given numbers? Oh yeah, we're given, okay. So 3 and 5. And I'm using 10 for G, which we're always allowed to do in these kind of situations, as long as we're not in the lab. All right, okay, so I did that. I'm just looking at the chat. I'm going back and forth between the screens. Okay, so that's that for that. Then it says, so now it wants to know the horizontal acceleration of the two block system. Well, so now I'm looking at the I'm looking at the x-axis now. So on the x-axis, we have, oh, and let's, since the thing goes to the left, apparently it accelerates to the left, let's call the left positive and the right negative, since apparently this thing is pulled to the left and apparently it accelerates to the left. So I always like to line up my positive x-axis with the expected direction of positive acceleration, right? So I think we've got tension minus Fk equals ma. Now we're told here, I mean, this is a little, right? A hand exerts a purely leftward force of 10, it just does. So, okay, 10 newtons. And then we're just told the friction. Normally, again, in the future, you'd have to calculate the friction from u times the normal, but here in this problem, we're told that it's 4 newtons. So M is total M, like 8, like 3 plus 5, right? So 6 newtons equals 8 kilograms times A. So A equals 0.75 meters per second squared. That's the answer to that. And now that you've got the acceleration, now it goes back to just regular kinematics. The whole point of getting the acceleration is now it goes back to the kinematics you learned before this unit. So, like, you want to know x now. Well, x equals 1/2 at squared plus v naught t, and it says that it started from rest. Oh, sorry. What? Yeah. All right. Approximately. We're going to 3 significant digits. Okay, so that's. Let me just look at this chat. I know we're running out of time. Anything in the chat? No. Okay. So that's that. And then, so the interesting thing is then now in F, and we'll end with this with F. I mean, F and G are like the same thing, but now that we've zoomed out, now we can zoom in our minds and calculate internal forces, so to speak, like the forces that one object is exerting on the other. Now that up until now, that was not even, we didn't even acknowledge that like in our original system schema and free body diagram, there's nothing about the two objects touching each other. We just treat them as one object. But now you see, we can zoom in. We could zoom in on M1. The free body diagram of M1 is, okay, normal up from the ground, from the table, the weight of that one object down, the tension pulling it to the left because the hand is touching that block, and well, that's interesting. Actually, one second. Oh, that's interesting. I've been assuming, okay. Sorry, hold on. I'm looking at the time. Oh, sorry. The hand, sorry, I misread the problem. The hand, it doesn't change. It doesn't change any of the numbers or anything, but actually, I apologize. The problem actually says that the hand is pushing M2, not pulling M1. It doesn't change any of the numbers thus far, but I better change it now. And I know the clock is about to, I know it doesn't change any numbers. I'll just pause on this. I know the class is about to end. It says that actually there's a hand pushing. And oh, that is one deformed hand. That's kind of gross. There's a hand pushing that way. Everything's still as we said, but it's a hand push rather than a hand pull. And why does that make a difference? Because, and we will stop at this right now, because then on M1, the only reason M1 is going to the left is because M2 is pushing it. Nothing is touching M1 on its side. So the force on M1 is the push from M2. That's what this problem wants you to. And how do we get that? How can we possibly know what that is? And we'll end. We're end right now. The push from M2. Push from M2, that must equal MA of M1. In other words, the push that we're solving for must equal, and literally, again, this is where we're ending, 3 times that acceleration that we already solved for, 0.75. So the push from M2 onto M1 must be 2.25 newtons. We'll end there. No new homework. Just everybody keep catching up, including me. Thank you for your patience and your everything. Sorry, Melita. I'm sorry. I see your hand. I don't know how long your hand's been up. I'm sorry. Everybody can go if they want.
It's okay. You answered my question already. Thank you, though.
Oh, I did. Oh, okay, cool. Okay, that's good. All right, I'm turning off the recording. I'm not going anywhere. Thank you guys. I mean, I'm here, but I'm turning off the recording, and I'm